What is this molecule? Assuming that the gray atoms are carbon and the white atoms are hydrogen. Ethane, right. We got 2 carbons, 6 hydrogens, and that's known as ethane. So we've seen that, we've saw that on the exam, we've looked at this a little bit. What we're going to deal with now in this next chapter, and this will be kind of the topic for the rest of the semester, is what happens when instead of a single pair of electrons shared between the carbons, we have 2 pairs of electrons shared between the carbons. So I'm going to draw that in this program. Here you see ethane. Position here. So I'm going to draw an additional bond here, and we're going to talk about what changes. So if instead of a single bond, we have now a double bond, okay, that means 2 pairs of electrons are shared. What else has changed about the molecule now? Take a look at it. Oops, let's go all the way around here. If we see that molecule now is the 2 carbons are sharing 2 pairs of electrons. What else has changed? Previous construction. Yeah, there's 1 less hydrogen on each side, and that's important. Why is that? Why did that hydrogen disappear when we made the double bond? Right, because if they still had that extra hydrogen, there would be too many bonds on each carbon. Carbons only have 4 bonds. So when we have that double bond, we now have fewer hydrogens on the carbons. What about the shape? How does the shape change? If you think about the geometry we talked about last time, or in the last chapter, versus this kind of a geometry, how is it different? How would you describe the geometry around the carbon atom? They're all in the same plane, right? So let's again, I don't know if I can put these things. Yeah, I can put them side by side. So here's let's do it this way. So let's have them both kind of spinning around here. May be a little too much for my computer to handle, but we'll see. But you can see clearly the difference in geometry, and that's really the important. Well, all the differences are important here. But you see the difference in geometry, you see the difference in the number of hydrogens. Here on the left in ethane, you see the tetrahedral structure with those 110-degree angles and that kind of 3-dimensional arrangement where one of the bonds is coming out at you and the other one's going back. And then over here on the right with the double bond, all of the atoms are now on the same plane. Everybody see that? Okay. Let's make a list of those characteristics. So the molecules we looked at last time were called alkanes, and the double bonds are called alkenes. So if we look at ethane, C2H6, if we try to draw the structure in 3 dimensions, looks like this. And then with the alkene, when we add that double bond, we now have C2H4, and we call that ethene instead of ethane. But because of, it's a common molecule, we often refer to it by its more common name, which is ethylene, rather than ethene. And it is flat, so we don't have to use the dash and wedge notation for that. We draw a double bond, two shared pairs of electrons. And there's our alkene, our double bond. Right. So these bond angles are about 110 degrees. These are 120. You have fewer things there, so they can spread out a little bit, and they can be planar. This is what we call tetrahedral geometry. And this is planar, but the official term for it is trigonal planar because of the triangle kind of thing, three things attached. So if we look at a given atom like this carbon atom, the things attached to it are at the corners of a triangle, and they're in the same plane, so kind of a flat triangle. That's where that word trigonal comes from. And planar, flat. Now there's a third thing that we don't really see just by looking at the structure, and that is the ability of the bond to rotate. So the carbon-carbon bond in an alkene can rotate around. And the consequence of that is that a structure like this is the same as a structure like that. Those two are the same things. Because what those represent is rotation around this bond right here. If we flip that thing over, we get this. And that's why when we were looking at, there are a couple questions on the exam like this, are these structures the same or are they isomers? We have to think about the longest continuous chain in any direction going anywhere, because the ability of these to rotate means that those molecules will always be the same. So if you have 5 carbons in a line, like both of these, that's pentane, no matter how it's written or how it's arranged. And we also wrote that like this. Right? Various ways. Any way you can write 5 carbons in a line, you got the same structure. It's the same thing. Well, double bonds cannot rotate. The way that second pair of electrons gets shared kind of locks it in a certain orientation. And so that bond cannot rotate. And what that means is that if we take two structures that have a double bond in them, but that have a different three-dimensional arrangement, they're actually different molecules. So let's take our C double bond C. And draw a structure like this. Versus this. And these are not the same. In this case, you can see the hydrogens are sort of opposite each other. If we draw an imaginary line through the middle, you can see the hydrogens are on opposite sides. Now, if we could just twist that over, we would get this, and they'd be on the same side. But because it's a double bond, we can't just twist it over. It's stuck in that configuration. And that means that those are different molecules. And we have actually special names for them. So we should say here, these were all the same. And these are not the same. Anybody know what the names are that we give the different orientations? Let's look at them in line structures here. So the line structure of this would look like this. And this one would look like this. Now, if it weren't for those double bonds, those two would be the same, because they'd be 4 carbons in a row. But because the double bond locks that rotation in place, those become different molecules. And the one where the similar groups are on opposite sides is called trans, and the one where they're on the same side is called cis. Trans means opposite, cis means same. So we can look at alkenes at these double bonds and determine whether it's the trans isomer or the cis isomer based on what side they're on. Again, there isn't a similar version of this for the alkenes because the alkenes can rotate and those would be the same. Or alkane, the alkanes can rotate and that would be the same. When we go to the double bonds, they're different, so we need to name them differently. And then the other part of this is finishing up the actual naming. Now, we talked about naming substituents at length in the last few weeks. Now, we want to continue that, but add what happens when we have an alkene in the structure as well. So let's look at the names of some alkenes, and then we'll add in this trans and cis stuff too, and we'll practice it. Well, the good news is naming alkenes for the most part is the same as naming alkanes. You find the chain, you use that as your basis, and then you put in your substituents. A couple special rules when it comes to alkenes. First, the main chain must contain the double bond even if it's not the longest chain. That's a little bit different. So if we see something like this, like this structure, normally if this were just an alkene, we would say that the longest chain is here, 1, 2, 3, 4, 5, 6. But because of this rule, the double bond has to be in the main chain. We have to actually take this as the main chain, even though it's a little bit shorter. It's only 5 carbons. So even though that's a shorter chain, that one gets the main name because it has the double bond in it. Secondly, we have to change the end of the name a little bit. Instead of something ending in -ane, it's going to end in -ene. So alkane, alkene, the name ends in -ene instead of -ane. So given that, what should that main name of this chain we just looked at be now with the double bond in it? So we say, how many carbons does it have? 5. And it's an alkene instead of an alkane. So the main name for this becomes pentene instead of pentane. And then the only other rule, well, the other part is to name the substituents as normal. So what is the substituent on this chain? What kind of a substituent is it? That would be right here. That's an ethyl. It's got 2 carbons. And what number carbon is it on? Is it attached to on the main chain? 2, right. So this becomes 2-ethylpentene. The only things we changed then are the main chain. That was the big change, because instead of looking for just the longest one, we need the longest one that has the double bond in it. And we changed the end of the name from ane for alkanes to ene for alkenes. Okay, there is a third rule. It didn't come up in this example, so we'll look at another example. The third rule if the double bond doesn't start at the first carbon, carbon 1, and it would be a long explanation. I'm just going to say number it, and I'll show you an example. So let's look at the structure that we drew up there before, this one. What is that molecule? Or what is the how big is the chain, the main chain here? 4, right? So what is that name? Butene. Let's put that down here. The problem with that is that there's another way we can make butene. Besides the cis-trans thing that we talked about earlier, we can also draw this. We can put the double bond there. That's also butene, right? It's a 4-carbon chain with an alkene in it. But we want these names to be unique. We want to know exactly what molecule we're talking about. So we use a number right before the main name to tell where that double bond is. So on this carbon, the double bond starts at carbon number 2. And at this molecule, it starts on carbon number 1. So we call this one 2-butene, and we call this one 1-butene. That way we can differentiate them. Now, in the case where you can have the 2 sides, whether the hydrogens are on the same side or whether they're on opposite sides, we also have to signify in the name whether it's cis or trans. So our fourth rule is what we talked about earlier. If it applies, which sometimes it doesn't, sometimes it does, we have to say cis-trans. So in this case, these are, if we draw a line through that middle, through that double bond, right along with it, and we see that the other groups are on opposite sides, then we call this trans. So this is trans 2-butene. What about this one? Do we have a cis or trans there? Actually, we don't for this one. If we draw that line through here, you can see a group on this side, but on this side you have the same thing on both sides. It's 2 hydrogens coming off of there. So there's no difference on either side. And that means that the two different possibilities are actually the same. And since there's no difference, we don't need to, or we have no way of determining whether there's any cis or trans, so it's not meaningful there. So those are the basic rules. Let's go through some examples and some practice and see if we can figure this out. All right. Let's try this one. What is the longest chain here? Where do you get 5? So like 1, 2, 3, 4, 5? Okay. Good, except we actually still count this whole chain. So if you look at that rule, the main chain must contain the double bond, but it doesn't have to start at the double bond. So if you can make a longer chain that contains the double bond, that's still the better choice. But you're right to contain the double bond. So the better chain is to go 1, 2, 3, 4, 5, 6. That's a continuous long chain that contains the double bond at the lowest possible number. But what is that type of chain called? How would we name that chain? That would be a hexene. And what about the number? Do we have to number where the double bond starts? Right, so this would be 2-hexene because the double bond starts at carbon number 2. We could put a double bond anywhere along here. Those would all be different molecules, so we have to specify that it's where the double bond starts at carbon 2. It's 2-hexene. What else do we need in this name then? Hmm? The substituents, right. What are they? Right. So this is 4, 5 dimethyl 2-hexene. Is that it? There's actually one more thing we need here. Trans or cis. So what is it, trans or cis? What do we think? How do we figure that out? Look at the double bond. And look at each carbon and the things coming off of it. Are those things coming off of it on the same side of that line or the opposite side of that line? What? The opposite. So what does that make this? Trans. Good. Okay. Let's try another one. Actually, hold on, let's do it this way. Go through those same steps and see if you can find or find something on your own now, and then we'll get it together. Anybody got a name for this one yet? Got it? What do you think? Well, yeah, that was what you're supposed to be doing. Did anyone else write it down or part of it? You don't have to have the whole thing. You got part of it? One, three. Dimethylpentene. Okay, anybody get something different? Did you get the same? Oh, you put a 1 here? Yeah, you don't actually need the 1, but it's not wrong either. That's okay. Is there a better name? So you went with cis here, and you said, what was yours? Cis. Okay. These are both close, but not quite right. So once again, we have to think about where our main chain is and how we count it out. So the main chain has to contain the double bond, but it also has to contain the longest possible continuous chain of carbons. So that's right. So we have to start down here and go 1, 2, 3, 4, 5, 6. All right, so you got it first. That's good. That's good. Yeah, so these are good guesses, but it really should be, and good job finding the cis also, because that's true. This should be cis 4-methyl 2-pentene. Hexene, yes, after all that. I got it wrong too, okay. Hexene, 6 carbons. Cis 4-methyl 2-hexene. All right, let's try another one. See if you can get this one too. You got this one yet? What do you think? Want to get something different? You get the same thing? Anything else? So that makes this your longest chain. Okay. You got trans. Well, let's look at it. We draw the line through there, and we look at the groups on each carbon that are the same. In this case, we can either look at the methyls or the ethyls. And are they on the same side of the line or the opposite side of the line? Opposite. So that means trans is the better name here. Trans 3,4-dimethyl 3. Now sometimes you encounter things where it's not clear if it's cis or trans because there are different kinds of groups on the two sides. Like what if there's a methyl on one but a bromine on the other? how can you compare those and say what's cis to what, what's trans to what? In those cases, we have another naming convention that we're not going to get into in this class called E and Z. But we'll stick to the cis and trans versions for now. Okay, let's try another one. Yeah, it's trans. Okay. So this one, the main rule to remember, the rest of it's going to look the same. The main rule here would be that we want to number the ring such that the alkene has the lowest numbers. So see how you can do that. So the double bond has the lowest numbers. Who's on this one yet? What do you think?
1,6.
Okay. 1,6. Okay. Others. What else did you get? Okay. Others? Well, yeah, let's look at this. So we know that we want the alkene, the double bond, to have the lowest possible number. So we're going to start at 1. But the other rule that if we look at how chains are set up, the double bond has to be, if we say that the double bond is at 1, that means it has to be between carbons 1 and 2. So if we say 1 cyclohexene, that means it's between 1 and 2. Just like if we say 3 hexene, that means that that double bond is between carbon 3 and carbon 4. Right? So it has to number continuously through the double bond like that. Which means the best way to number this is 1, 2, 3, 4, 5, 6. If we started here and went this way, then the double bond would be between 1 and 6. And that would be not clear in the name. Yeah. So that's right.
You don't have to like.
You could also do it this way.
Right.
You could also go 1, 2, 3, 4, 5, 6.
But do you have to put a number in front of cyclohexene or no?
In this case, you don't because it's at 1.
Okay.
And according to the rule, if the double bond doesn't start at the first carbon, number it. If it does, you don't really need to. So we could just call this butene. But sometimes it's nice to have in there just to be clear. So the better name here would be 3,6 dimethyl cyclohexene or 1 cyclohexene. What about cis and trans here? That's right, it is cis. However, we don't usually put the cis in the ring. Anybody know why? If it's in a ring, why we don't do that? It's because the trans one wouldn't be possible. If you think about that ring structure, if we had to draw a structure, remember trans would look something like this, right? If this is cis and this is trans. So if we tried to connect that ring, you know, it wouldn't really work. The geometry wouldn't work out inside that. There's not enough space. It would stretch the bonds too much. So that doesn't work. So in these smaller rings, you can't have any trans double bonds. You can only have cis. And that's why we leave that out. It's not wrong to put it in. If you said cis, that's fine. But we usually don't put it in there just because that's the only possibility. Any questions about that? Okay. Let's look at one place where you see this is in, well, I guess we have to look at one more term. We've mentioned this before, but let's really define it. Saturated versus unsaturated hydrocarbons. Anybody remember what we're talking about when we talk about saturated or unsaturated molecules? It's not solutions at this point, it's talking about the structure itself. Yeah. What does saturated refer to? Like, what does that word mean in a non-chemistry context? Something is saturated. What does that mean? You might, if you went and stood outside for an hour, we might say that your hair was saturated with water, right? Or your coat was saturated with water. What does that mean? I'm trying to say there. Or if we look back to saturated solutions from chapter 7, what does it mean for something to be saturated? No. Just like full, right? As much as could possibly be in there. If you stood outside and you were getting a little bit wet, you would probably say you were saturated at the point where the water wouldn't even absorb into your clothes anymore. It would just run off because you had so much water already in them. So saturated means the most possible of whatever that you can add to something. And in this context of organic compounds, it refers to hydrogens. Per carbon. If you look at alkanes, let's say we have a 3-carbon alkane. The most possible hydrogens we can put there is if we stretch them all out in a straight chain and we fill the rest of the 4 bonds of carbon with hydrogen. And that ends up with 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. There's no way that you can arrange 3 carbons together in a molecule where you can have more than 8 hydrogens, because it would violate other, the 4-bond rule or something like that. So this is what we would call a saturated compound, a saturated hydrocarbon, because it has the most hydrogens that you can possibly have. So how can we have a compound that has fewer hydrogens than that? There are 2 ways that we can have compounds with fewer hydrogens. Double bond or triple bond. So if we put extra bonds in here, now we have something like this. Now we can't quite fit as many hydrogens in there. If we count that up, that's now C3H6. Unsaturated. And what's another way we could do it? There's one more way you can make unsaturated compounds besides multiple bonds. Any idea what that might be? You could put them in a ring. So if you make a cyclopropane and you fill the carbons with hydrogens so they each have 4 bonds. This is also C3H6, so that's also considered unsaturated. And we use these terms, or we see these terms sometimes when we talk about fats. So fat, anybody know what a fat molecule looks like? Have you heard of saturated versus unsaturated fats? So that's what this is referring to. That's what this is what that refers to. A fat looks like this. You have three carbons in a row. With then oxygens. And this is actually a glycerol molecule. If you remember glycerol from the last lab. Glycerol, if those oxygens had hydrogens attached to them, that would be glycerol or glycerin. So that's kind of the backbone. It's called a glycerol backbone. And then coming off of these are these molecules with carbon double bond oxygen, and then long chains of carbons. Usually 12 to 20 carbon chains. So if you've heard the term triglyceride, That's what that is. This is a triglyceride. It's got 3 of these big long molecules connected to glycerol or glycerin on the backbone. Now these individual parts of it, when they break off on their own, are the fatty acids. And depending on the makeup of those chains, they can either be saturated, meaning straight chain like they are here, no double bonds, or they can be unsaturated, meaning that they have the double bonds. So this would be a, let me see if I can find a picture. Oh, I'll have to look at it next time. So this would be a saturated fat. An unsaturated fat has a very different shape. So a saturated fatty acid, like say stearic acid, looks like this. It's a long carbon chain. We know that it has the zigzag geometry, but it kind of stretches out straight. So that would be a saturated. The reason it's a fatty acid, because it has that carboxylic acid functional group on the end. But an unsaturated fat looks kind of different. So this is oleic acid, which is the main acid in olive oil. And it's unsaturated because of this double bond here. It doesn't have quite as many hydrogens as it could. If we could turn that double bond into a single bond, it would have, it would be more saturated, it would have more hydrogens. What's the type of alkene there? What is the geometry of it, what we call stereochemistry? Is it cis or trans? Close. Yeah. Once again, we look at it this way, we draw the line through there, you see the big parts are on the same side, the hydrogen's on the other side. And this has a cis alkene in it. And in fact, all naturally occurring unsaturated fats are cis. Now this has big consequences for the geometry, as you can see here. A saturated fatty acid is a long, stretched out chain. An unsaturated fatty acid has this kink in it. And that means that it's going to have very different physical properties. So saturated fatty acids, what do we know about saturated fats? How are they different physically than unsaturated fats? They're usually solid, and unsaturated fats are usually, or are often liquid, like olive oil is a liquid, butter, which is higher in saturated fats, or lard is a solid. So when this chain is kinked like that, the fatty acid chains, or the fats, the triglycerides, can no longer line up with each other quite as nicely. So the intermolecular forces aren't as strong, and that's why they're liquids instead of solids. Now there's a process that's important in chemistry called hydrogenation. What do you think that means? Adding something. What do you think we're adding? Hydrogen, right. In hydrogenation, you take an alkene, like we can just take ethene for now, and you react it with hydrogen, H2, and a metal catalyst, and you add those hydrogens to the molecule. So you're really turning an alkene into an alkane by adding hydrogens to it. And this is kind of how it's drawn. We start with the molecule, and then we say we add the hydrogen with the catalyst, and we end up with more hydrogens on our molecule. We do this to fats to make saturated fats from unsaturated fats. This is where things like shortening come from, where you have something that is an unsaturated vegetable oil. You hydrogenate it, turn it into a saturated chain. Now it can line up with the other saturated chains more closely and have a higher melting point and become a solid. But one other byproduct of the process is that you can have what's called partial hydrogenation, where instead of actually fully hydrogenating like this, you simply partially hydrogenate and you actually flip those double bonds. And that's where we get what we call trans fats. Trans fats come from cis fats that have been partially hydrogenated and made to stretch out. And there's a lot of evidence that trans fats are really, really bad for you. So we don't use them so much anymore. They're still around here and there, but most people are trying to get rid of them because they're really not good. They have all the problems of saturated fats in that they're solid, they can contribute to clogged arteries and that kind of thing, but also they are somewhat reactive because of that double bond. So they get into places that reactive fats are not supposed to get into and can cause some damage. All right. The other thing you may have heard, and I guess we'll talk about this more next time. If you hear about different types of unsaturated fats like omega-3 fatty acids or omega-5s that come from fish oil and other places like that, that refers to the position of the double bond on the chain. So if the double bond is 3 from the end, that's called an omega-3 acid. If it's 5 carbons from the end, it's an omega-5. If it's 7, it's an omega-7. That's where that terminology comes from. Where that unit of unsaturation, that double bond, is on the chain, changes how your body uses it and what your body uses it for. That's where those terms come from. All right, questions about that stuff? What's your favorite cooking fat? If you had to pick one. You don't really cook? Okay. Anybody cook? Nobody cooks? What? Butter? It's a good favorite. What? Or olive oil. Another good one. Yeah. Bacon fat. Anybody cook with a lot of bacon fat? No. Lard. Oh, okay. You're what? Eating bacon? All right, well, on Tuesday we will finish this up talking about some reactions of alkenes and alkynes, which are the triple bonds. So have a lovely weekend, and I'll see you on Tuesday.